Welcome back to The Explainer, everyone. Today we're unpacking something that feels like it's pulled straight out of a sci-fi movie, but I promise you it is very much our impending reality. We are talking about space colonization and the biological impacts of leaving Earth. You know, as we look toward the Moon, Mars, and beyond, we really have to start asking some incredibly profound questions about what spaceflight actually does to the human body, and not just to the travelers themselves, but to the generations that come after them.
Think about it. It is the ultimate high-stakes question, right? Can humanity actually safely reproduce in space? Up until recently, the data on this, especially when we're talking about mammalian biology, has been pretty anecdotal or just restricted to super short exposures. But today, we're diving into a genuinely groundbreaking study from the NASA Rodent Research 20 mission that tackles this exact mystery head-on. Honestly, the findings we're about to look at are going to completely rewire how you think about our extraterrestrial future. Okay, so let's kick things off with Section 1, the space colonization dream and the biological hurdles standing in its way. So picture this. We already know spaceflight comes with a brutal set of hazards: microgravity, intense radiation, that crushing hypergravity during launch and reentry, the whole shebang. And while we've got decades of data on how human bodies handle those stressors, there has been a glaring, almost shocking lack of data on the female reproductive system. We know astronauts survive, but what about the reproductive consequences? To finally get some answers, researchers designed an experiment. They sent 20 female mice up to the International Space Station, where they spent 42 days floating in microgravity. Now, to put that into perspective, 42 days for a mouse is roughly equivalent to about 8 months of a human woman's menstrual cycles. That's a huge chunk of time. Afterwards, these flight mice splashed back down to Earth, got just 5 days to reacclimate, and then were bred with normal Earth-bound males. Researchers then compared them against ground-control mice living in identical simulators here on Earth to see if these space-flown moms could successfully establish pregnancies.
Moving right along to Section 2, let's look at the spaceflight mothers themselves. This is basically the tip of the iceberg.
At first glance, the data looked absolutely fantastic, literally incredibly reassuring. These initial mothers bounced back remarkably well from their space trip. Their ovarian response was completely intact, and their bodies successfully reestablished a normal endocrine axis, which basically just means their biological communication systems synced back up perfectly to allow for ovulation. Early embryonic implantation worked just like it did for the earthbound mice. The only tiny hiccup was a super minor decline in their birth rate, maybe about 1.5 fewer pups per litter, but by and large they delivered live, healthy-looking babies. It turns out the female reproductive system is incredibly resilient once it gets back to Earth's gravity.
But, and this is a massive but, the true impact of spaceflight, it was actually hiding in their children. Which brings us to Section 3, the offspring shock, because this is where the transgenerational stuff really hits the fan.
This is where the whole explainer takes a wild turn. We are shifting focus from the mothers to the F1 offspring. The heavy biological toll of microgravity basically bypassed the moms entirely and struck the kids, mice that had literally never been to space. And what's fascinating is how highly sex-dependent these inherited traits were. The female offspring developed increased body weight and fat mass compared to ground controls, while the males showed zero change in body composition. Behaviorally, the females were way less anxious, bearing 37% fewer marbles in standard anxiety tests, while the males just acted normally. But physically, those F1 males developed a significantly higher soleus muscle mass. So the mother's spaceflight exposure manifested in completely different ways purely depending on the sex of her babies. But wait, it gets crazier. Despite those striking differences between the males and females, both sets of offspring shared one invisible systemic weakness. When researchers tested their soleus muscle, which is a key postural muscle that gets heavily degraded in microgravity, both sexes showed a significant drop in specific force. Basically, their raw muscle strength was compromised. This is a huge deal because it brilliantly demonstrates a tangible, physiological impact on mice that never once left Earth. It strongly points to the idea that the intense stress of spaceflight actually reprogrammed the mother's germline, passing down these microscopic epigenetic scars directly to her pups.
And sadly, those scars didn't just stop at muscle strength. For the female offspring, it severely impacted their ability to create the next generation. We need to introduce a critical term here: premature ovarian insufficiency, or POI. Basically, this is an early loss of fertility caused by a damaged ovarian reserve. Researchers measure this using something called anti-Mullerian hormone. Shockingly, the F1 female offspring from the spaceflight lineage had significantly lower levels of this hormone at just 21 days old. Their ovarian reserve had already crashed right out of the gate.
When you map out this biological reality over a 9-month breeding trial, the data is just stark. Initially, the F1 females from the Spaceflight lineage kept pace with the others, but as time went on, their reproductive numbers essentially fell off a cliff compared to the normal Earth-bound lineages. They suffered a premature loss of fecundity, pumping out fewer litters and significantly fewer total pups. It's as if the biological clock for these spaceflight offspring was just permanently stuck on fast-forward. Let's move to Section 4 and see how this cascades. The F2 generation, the grandchildren effect.
Okay, we are officially in the deep end of the pool now. What happens when those affected F1 kids grow up and have children of their own? We're talking about the F2 generation, the grandchildren of the original space-flown mice. You'd think the effect would fade, right? No way. The transmission of that biological vulnerability didn't stop at one generation. When scientists checked the ovarian reserves of the young F2 females, they found that they, too, were significantly reduced compared to the ground control families. The toll of microgravity was literally echoing down the family tree.
But the researchers weren't done. They wanted to push the envelope. While the baseline differences in these grandchildren were somewhat subtle, the team decided to introduce a secondary stressor, a high-fat, high-sucrose Western diet, just to see if there were any hidden metabolic dysfunctions waiting to be triggered. And oh boy, did it expose some hidden flaws. A vulnerability completely unique to the spaceflight lineage suddenly flared up. Under the stress of that high-fat diet, the F2 grandchildren reacted completely abnormally compared to normal Earth mice. The F2 males from the spaceflight line just blew up, gaining way more weight and fat-free mass than their ground control counterparts. But on the flip side, the F2 females totally failed to gain the normal fat-free mass that you'd expect to see. It's wild. It proves that the initial spaceflight exposure had this lingering, transgenerational metabolic impact. It permanently altered how these grandchildren processed energy and built their bodies 2 whole generations later. Which brings us to our final section. Section 5, our extraterrestrial future, and what all of this means for us. So let's talk about the so what of it all. What does this mean for actual human space exploration? Well, the implications are honestly massive. Right now, female astronauts average around 38 years old on their first mission. At that age, reproductive capacity is naturally starting to decline anyway. If spaceflight induces the kind of early reproductive aging we just saw in these mice, it could absolutely trigger premature ovarian insufficiency in human astronauts. Researchers suspect that the hub of all this chaos is mitochondrial dysregulation, basically the powerhouses of our cells just freaking out under the stress of space. All of this points to an absolutely urgent need to develop serious biomedical countermeasures to protect astronauts before we even consider building long-term colonies.
I want to share a quote directly from the researchers because it really hits the nail on the head regarding the weight of these findings. They wrote, "Although the female reproductive system may be functional after spaceflight, biological vulnerabilities can still transmit to next generations." Honestly, that is a sobering conclusion. The parents might survive the trip just fine, but the biological receipt gets handed directly to the children.
And that really leaves us with one massive ultimate question we have to answer as a species. Before we head out to colonize the stars, before we set up shop on Mars or the Moon, how do we protect the generations that haven't even been born yet? How do we ensure that our grand dreams of the cosmos don't come at the hidden, invisible expense of our own descendants? It's a completely fascinating puzzle, and one I guarantee scientists will be racing to solve over the next few decades. Keep learning, keep questioning, and thank you so much for joining me on this explainer.